Okay, good morning, everyone. Thanks for coming. So I'd like to reflect also a little bit on my session, which was titled Systems and Algorithms. As you already saw, the previous session really shifted into system discussions, which clearly tells you that my session was the most important one. So that said, though, just a general observation and memo for the committee, I think we were very weak on algorithms. People did talk about systems, but some people explicitly said to me, we can't talk about the algorithm, sorry. But we had some systems examples, and so let me just quickly remind you on who even showed up. So we had Bill, Edwin, Dennis, Charles, Kison, just in case you forgot. And I want to reflect a little bit with the next few slides on what some of my take-homes were. And if you don't know me, I'm actually a custom IC designer. I'm more in the hardware camp, actually. I like to fiddle with transistors and so on. And so my heart is bleeding on the next slide when I say that this may actually not be the most important thing when you think about systems. In fact, I think one of the take-homes that I got from the session was that, at least in the short term, the biggest leverage you will have from using existing, or what I would call mildly customized hardware solutions, and really figure out what the problems are, what the markets are, where the volumes will be, drive algorithmic innovations, maybe settle all these questions about frameworks, specifications, and so on. And then going further a little bit into this, I think there's a lot of fundamental questions that don't even have much to do with hardware. And Bill brought some of these up, and I will go into this. Just to clarify, what do I mean by mildly customized? So I'm an academic. So for me, something fully customized would be sort of a nano quantum bio brain inspired little thingy. Is that what the system designers want right now? No, I don't think so. We have a lot of other questions to resolve before that stuff will save the day. We're not held back by that. And so that's basically my point. So instead, what you may want to do is use an ARM processor or build something around it and so on. That's what I mean by mildly customized. And I think the Qualcomm example is sort of in this camp. I mean, yeah, you have maybe a custom chip and so on, but it's a relatively conventional approach that is sort of mildly customized from what ML wants to do. In terms of system components also, I mean, this is with these yellow boxes stolen from Evgeny's intro slides. We have a lot of these system pieces, and we had a talk about the camera modules, which are low power, that has been driven actually by other applications like mice and wearables and so on. We have a lot of good components, and we should use them to drive the system development. I think that's also a very important point. Going a little bit more detail on kind of doing things with existing hardware, of course, I should highlight some of the stuff that we do in this space, and this is my student Albert's poster that's over there. What can you do with existing hardware? Can you be clever about how you do the convolutions and how you sort of work with the memory and avoid stale bytes in that memory and so on? And so what can we squeeze into, say, a 2 kilobyte footprint or a 10 kilobyte footprint and so on? I think these things are really important for a system designer. And again, this doesn't require you to necessarily design a new chip right away, but the findings you get from these kinds of study may influence how you later design custom systems. And so I think this is a very important aspect of the game. Beyond this, and here I want to just flash by a picture from Bill's presentation, there's a lot of fundamental questions that have almost nothing to do with the way we build the hardware. What happens when we bring a lot of these nodes together, and how do they interact? How do we connect them? How could this lead maybe to swarm intelligence? No one mentioned this yesterday, but there's research on this, right? It's not just one node. How do they talk to each other? How do you maybe do some inference that fuses information from all of these nodes? These are system level questions that ultimately may not care how the node is implemented. And then to me, one of the big gorillas in the room is really this lifelong learning, or learning to learn. We're completely hung up with supervised training right now. I don't think that will be the end game. Maybe it will be a mix of supervised training and then maybe some refinement in the field. How that's done, I don't know. If you guys have figured this out, you should tell us about it, but I have no idea how to do that. And I think these are really big system level questions that can also be answered probably with existing hardware. So then once we've answered all these things and we have maybe good ways to spec systems and we have frameworks and so on, maybe then we can drill down, and then maybe there's a sort of a break in this chicken and egg problem, right? Maybe we find this big killer apps, and then there can be a lot of customized tiny ML systems, but it's very difficult to see the eggs come in before the chicken is there. So that's basically my view on this. Although, right, it should be somewhat of a parallel process, and that's why the work by Dennis Sylvester and others, many others in this space, that are really trying to probe the limits and how small can we make this, how many nanowatts can we drive certain functions to, if we fully customize and forget cost, forget volume and all this, right? Let's just make a plot on the Pareto curve that drives all of this into the extreme so that we're informed about what these limits are. So this is going on in parallel. This is very useful, but I don't think this will necessarily shape the market, right, or the deployment in the next few years. So these were my personal take-home. Here's a quick summary of it. I think a lot of the conceptual stuff can be done with existing components, mildly customized hardware, cores, and so on. And we saw this huge spectrum in the hardware session. And in parallel, many academics work on highly customized solutions, and then industry has maybe something in between. But to me, and I think maybe next year we could do a little bit of a better job of bringing people in who talk more about algorithms that tell us how we learn in the field, how we do swarm intelligence with these nodes. And interestingly, also something I didn't hear, I think, all day yesterday, or maybe I missed it, but security, privacy, and so on. These are also very important questions that we need to think about, and these are very high-level, system-level issues. So with that, I also want to open up for questions and discussions. Kurt.
So I like your chicken and egg slide, and I think that's very much the question posed to all of us. Do you see that we're just a factor of 10 away, or 2 away, or 5 away, or sorry, put it this way: with a factor of 2, 5, or 10 improvement in some fundamental factor, say power efficiency or energy efficiency on computations, then here's the app that people have been waiting for. And the reason I'm getting at that is I'm trying to understand, is this a poverty of imagination, or is this a clear technical problem?
So do you mean for existing processors, digital processors, or?
Okay, so I've already bored you on our conference calls about my pantry moth going by a motion detector and ruining my Hawaiian vacation, wondering what the heck went wrong at home with the alarm system going on. Now, is my failure to have, from your perspective, is my failure to have a little camera there with enough intelligence to actually detect that's a pantry moth and not an intruder, is that just a good old down-home technical problem that we're just a couple years away from solving with your good work and other work in the complete stack? Or are there more fundamental issues about finding that killer app to really make this a viable economic endeavor?
Yeah, this is a very tough question. I don't think I have a good answer to that. I want to forward it to the audience. Here's one.
I think the fact that there's a small number of people here in the room, these are the people that can actually build a neural net, implement it, and get a result. When it's easy enough so that 10x more people than are here can start building these, I think you'll start seeing those 10x more people come up with more interesting ideas. I think there's a lot of ideas, but you need to get 1,000 more people out there that are actually thinking about them, 10,000 to come up with the idea that I've never even thought of. Somebody looked at a garbage detector like they did in Barcelona. I always thought it was laughable that you'd want to put a garbage level detector. I just seemed, really? Well, it turned out it saved a lot of money, and somebody had the guts to do it and show it was useful. Someone's going to look at something I've looked at all my life and thought, you don't need to. and they'll come up with something interesting. You just got to make it easy enough for them to do it.
Yeah. Other points. Maybe Evgeny can be an icebreaker. I mean, so your perspective on this whole Qualcomm system, I think it fits my perception, or am I missing something in terms of how you guys think about this?
I think what I heard here several times, it's really, to me, it's a top-down. I think Kevin said it too, that once we have like a killer app, and the more people we have thinking about killer apps or in general apps, that will drive a tremendous pool of things, and then people will start optimizing, people will start using existing software, new software. I think we need to have more this kind of, doesn't have to be killer, but more
more app.
more app, more use case.
So I feel like I've been talking too much. I was trying to resist this one.
But it's so important.
I know. I mean, from our perspective, like you might have seen that Google just released server quality on-device transcription for the Pixel. And, you know, I think that that's in the realm of like 100 megabyte-ish sort of model. So that is showing that you can actually do, you know, sort of cutting edge quality speech recognition on a local device. Now that's running on an SoC, on a high-end ARM thing. If we can get the cost and the energy efficiency of running high quality speech recognition down to something that fits on like a 50-cent chip that runs on a battery for a year, people will throw that into billions of devices. I mean, so for me, that's one of the motivating use cases, is that we've seen this proof of concept through Alexa and, you know, all of the other applications that voice interfaces work in a bunch of circumstances. If we can get voice interfaces cheaply and low energy into a whole bunch of devices, there's a clear demand for that. So if you're worried that these things won't sell, if you can get something that can do that, then we can be pretty sure that that's actually going to sell billions of units.
Last question, last comment. Yeah.
Thanks. So I wanted also to make a note that it would be always great to, when we develop the algorithms and networks, to pay close attention to how the network and layers are learning. And that highly depends on the applications. So over the past few years, you know, we've been looking to a lot of variety of different signals, you know, time series multimodal, biomedical signals, the RF signals, you know, obviously popular, you know, image, video, audio, but you definitely cannot use the same network architecture and expect to apply for all those different applications and, you know, achieve to that tiny ML hardware that you're guessing. Because, for example, variety of these tiny time series multimodal biomedical signals, you really don't need, you know, so much parameters or such a dense networks. You can actually reduce the number of parameters by 2 orders of magnitude or even 3 orders of magnitude, so, and therefore to achieve to microjoule, nanojoule efficiency. So I just want to make sure, I know we always talk about the scalability and programmability for a variety of different applications or different, you know, data, but I guess this is actually super important, which was also brought by TensorFlow group, that it's always good to look into the algorithms, networks, and somehow hack it, you know, so to get better energy efficiency.
Maybe we can do one more, Debu. Yeah.
Hi. Thank you for taking my question. I think what I was hoping to see, and this is something that I've always thought about for the last few years, learning on the device. You know, I haven't seen yet, but this has to come.
Yes.
The question is, how do we do it? Now, I'm in communications engineer by training for 30 years, but we always do, we do training and then we adapt continuously. The question is, the computation may be small, and the problem that's being solved in communication is probably doesn't require as much computation, it's only the channel being learned But here it's much more complex. The question is, here the training, as you said, the supervised learning is done once it's static. But then when it's deployed in the field, the experience that comes, how do we capture that? And how do we adapt to that? And that's the question I have as to how.
Yeah. Yeah, in comms, you guys are lucky. You have pilot tones and things like that, right? I wish we had an ML pilot somewhere so I can just continuously. But I think that's the key challenge in my mind. Anyway, I think this is the end of the session. Thank you.